Hello everyone and welcome back. In the previous video, we learned about variables, expressions, and equations. Today, we are going to talk about exponents and powers. Again, this topic may seem simple, but powers are everywhere in cryptography and zero-knowledge proofs. Whenever you hear things like 256-bit security, SHA-256, 2 to the power of 128, or equations like x squared, you are dealing with exponents. So before moving to more advanced topics, we need to become comfortable with powers. What is a power? Let's break it down. 2 to the power of 3 equals 2 multiplied by 2 multiplied by 2, which equals 8. So 2 to the power of 3 equals 8. Notice that the small number above is called the exponent and the large number below is called the base. In this example, 2 is the base, 3 is the exponent. Another example, 5 squared. This means 5 times 5, which equals 25. So 5 squared equals 25. The exponent tells us how many times to multiply a number by itself. Powers with variables. Powers don't only apply to numbers, they also apply to variables. For example, x squared. This means x multiplied by x. Another example, x cubed. This means x times x times x. So x is multiplied by itself for 3 times. Suppose x equals 4. Then x squared means 4 multiplied by 4, which equals 16. Why are powers important? Powers appear everywhere in mathematics. For example, area of a square is side to the power of 2, or volume of a cube is side to the power of 3. But powers are especially important in cryptography because many cryptographic systems depend on a repeated multiplication. A simple ZK example. Suppose I have a secret value x and I claim that x squared equals 25. If my secret value is 5, then 5 squared equals 5 times 5, which equals 25. A zero-knowledge proof can prove that I know a value satisfying this equation without revealing the value itself. Notice that powers already appear in very simple ZK problems. Understanding large powers. Let's look at 2 to the power of 8. This means 2 multiplied by itself for 8 times, which equals 256. Notice how quickly powers grow. Let's continue. 2 to the power of 10 equals 1024. 2 to the power of 20 is more than 1 million. 2 to the power of 30 is more than 1 billion. Numbers become huge very quickly. Why cryptography loves powers? Modern cryptography relies heavily on very large numbers. For example, 2 to the power of 128, this number is unimaginably large. It is approximately 340 on the zillion. Why is that important? Because if a hacker had to guess among 2 to the power of 128 possibilities, it would take an enormous amount of time. That's why we often hear terms like 128-bit security or 256-bit security. These security levels come directly from powers of 2. So powers are one of the reasons modern cryptography is secure. Rules of powers. Now let's learn some useful rules. Multiplying powers. Suppose we have 2 squared times 2 cubed. Instead of multiplying everything separately, we add the exponents. So 2 squared times 2 cubed equals 2 to the power of 5, which equals 32. Dividing powers. Suppose 2 to the power of 5 divided by 2 squared. When dividing powers with the same base, we subtract exponents. So 2 to the power of 5 divided by 2 squared equals 2 to the power of 3, because 5 minus 2 equals 3. Power of a power. Suppose 2 cubed raised to the power of 2. We multiply the exponents. So 2 cubed to the power of 2 equals 2 to the power of 6, because we multiply 3 with 2, which equals 6. Why this matters for zero knowledge. Later in this series, we'll study modular arithmetic, finite fields, polynomials, elliptic curves, and many cryptographic algorithms. All of these topics use powers constantly. If you are comfortable with exponents, those topics become much easier.